Okay, so let's look at this other generalization you did, that this integral converges if n is bigger than 1. So let's use the example of 1 over x squared. So this is the graph of 1 over x squared. So here's 1 and 2 and 3 and 4. Okay, so I'm going to be using right-hand endpoints. So the area of my first rectangle here would look like this, right? So f of 2 would be the height, width is 1. Then the second rectangle would look like this. Height of f of 3, width of 1. Third rectangle would look like this, right? So plugging in 2 into the function 1 over x squared, I get 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. So this, with rectangles of width 1, turns into this, right? Okay, so what do we see here? This 1 over n squared, right, which is this, which is the area of the blue rectangles, right, and they keep on going, is going to be smaller than the area under the curve of 1 over x squared. And notice I'm starting it at 2. So I'm starting at 2, and if I have this, so the area of the red for sure so what do I know about 1 over x squared, that integral? I know that this integral converges, so that must mean that the blue area underneath will converge also. So starting at 2. So since this one starts at 2, this one has to start at 2, and so to adding on a finite number, it's still also going to converge. So we can make the generalization that from 1 to infinity, this converges, so that means this converges. Okay, so this again, just trying to make sure you really got this, because we're going to use it a ton in the next section. So this is n to the 3 halves, right? Power over root. So this, oops, forgot my 1 to infinity. This converges by p-test. And this here, so you can pull the 3 halves off to the side. Power over root, this converges by p-test also.